Hi Level 3s, I'm going over the displacement, velocity and acceleration pages that I asked you to do on the last day of last term. These are the concepts that you were supposed to cover. So just to refresh your memory, if we start at equilibrium and we move, in other words, this object is going to move up on the spring through a certain angle of theta, and also through a displacement of y. Then the displacement phasor has turned by sine theta is opposite over hypotenuse, so it's this y over here. If I can find my mouse, y is opposite the angle over hypotenuse, which is a, and so we write it as sine theta equals y over a. If we rearrange that and we substitute in that we know that angular displacement is angular velocity times time, then we come out with this equation. And this equation is going to be used to find this displacement for the simple harmonic motion object when the timing starts at equilibrium. So let's look at the example on page 161, the second half of it. There's a pendulum swinging, and what the question says is that the period of the pendulum is 1.9 seconds. So remember that if the pendulum starts at equilibrium, swings all the way to the right, back to the left and back to the middle to the equilibrium position, that is one cycle. So that's the period of 1.9 seconds. So in other words, if you look at the phasor diagram, what I've done here is I've turned this pendulum on its side, which may seem a little strange, but you'll see that it helps to work with a reference circle. Let's just stop all these swinging pendulums. And the phasor, or the point then, will still start at equilibrium and go anti-clockwise, as it did with the oscillating spring that was moving up and down. So that's the reason I turn the pendulum on its side. You don't have to do this, but if you're going to keep it upright, then your position line through the center of the circle will actually be horizontal. And you have to rethink again where you're going to start your equilibrium. So for this one, I always turn my pendulum on its side so that I can work with a similar reference circle. So at equilibrium, the pendulum's here in the middle, the phasor is there on the right hand side, and it will now begin to move in anti-clockwise direction. The next phasor will be at the top, a quarter turn later, in other words 1.9 divided by 4, and then another quarter of the time it will be over here. So 1.1 seconds is going to be at least further than halfway, but not quite all the way to the 1.9 second mark, which is, so it's going to be somewhere in this quartile, I suspect. So what we're going to look at is finding y. What is this displacement here from the position where it's past the equilibrium again, returning in the opposite direction? We use the equation that we've just derived. The displacement is equal to a sine omega t, and we also remember that omega is equal to 2 pi over t. So we've got the period, and we can plug that number in there. We multiply it by 1.1 before we find the sine of this total value. So my suggestion is that you actually do that on the calculator now and check it. Make sure that your calculator is in the radian mode. Pause the video at this point if you can't remember how to get to radians on your calculator. And so you end up getting this value 0.0666 meters, and it's obviously going negative, meaning it's going in the opposite direction. Moving on to velocity now, just a reminder of circular motion. So when an object's going in a circular motion, the point P will be moving at a velocity that is tangential to the circle, and the magnitude of the velocity can be found using the linear and angular relationship V equals R times omega, where R is the radius of the circle. We will find the velocity phasor for the velocity of the simple harmonic objects. I've taken the object out of the way, the bouncing spring, so that I could enlarge the diagram. So again, we've got a point P here. The object has moved through a distance, and at that point P, its velocity is a tangent to the circle. And so if you look here, r times omega will equal a times omega, because here r is equal to a, right? So what we then say is, well, the object is bouncing up and down here. This is simply the reference circle. So what we need is we need to find the velocity in the same plane or the same parallel direction. We're going to find, in other words, a component of this velocity. And if you draw a triangle there, you will note that this angle here is the same as this angle here. So you can see the right angle is there in that corner, it's here in this corner. And so we can find, for that triangle, we can find that cos theta is adjacent over hypotenuse, which is v over a omega. And so we can rearrange and substitute in theta is equal to omega times t, and we end up getting this equation. So what this shows us is that the velocity is constantly changing, depending on what the position is around this circle. Because the direction of p is changing constantly, and so the length of this component will change constantly as it goes around the circle. To look at an example, we take the same pendulum. I remind you, it started it off over here at equilibrium. It moved to one side, and then the corresponding phasor went just so up to one side and back down. Remember, I've turned it on its side, and it's heading towards the left. In other words, in my turned diagram, downwards. And so we look at applying this equation we've just worked out. And please note that omega has repeated twice, so we have to apply omega equals 2 pi over the period twice. These two values must be multiplied together before you find the cosine value of them. And do it on your calculator now. Make sure you get the same answer. Note, we find that the velocity is a negative value, and so we know it is in the opposite direction. We have to interpret that answer. Just two things to note is that the velocity at the equilibrium and the end positions, remember when you have something moving to the end position, it's going to have zero velocity as it changes direction, but through equilibrium it's going to have a maximum velocity. So velocity there will be a times omega. There will be no sine or cos of anything at that point. And finally we'll look at the acceleration to find an equation for simple harmonic motion. But before we do that, let me just remind you of centripetal acceleration and what that means. When an object's moving in a circle, remember that the direction of the acceleration is always towards the center of the circle. And we can work that out because on the bottom here I've drawn these two vector diagrams. If I say vectors v2 minus v1, remember we put v2 vector and then we add the negative of v1, we find that the change in velocity, which is this purple arrow, actually acts towards the center of the circle, right? And so we know that the change in velocity, the change in time, gives me the acceleration, so it acts towards the center of the circle. And the size of that acceleration is v squared over r. And so again, we take the same particle at the same point to try and resolve what's going on here. So for centripetal acceleration, we just substitute in the a, and then the a omega squared, and we end up finding that acceleration is equal to a omega squared. Right, now for this particle at this point, the acceleration, as we said, acts towards the center of the circle, and the actual object, however, is moving in the direction that is parallel to its positions. Remember, the object is bouncing up and down here, and so we construct a component that is in the same direction as that, and a component of this vector. And remember, it's constantly changing. So depending on where this acceleration is, if it's up here, then this acceleration line will be a full length line. If it's over here, acceleration will be 0, and so on. So for the shaded triangle now, we consider that opposite over hypotenuse will be negative a over a squared omega, or a omega squared rather. And so if we rewrite that, we end up with this equation. A is equal to negative a omega squared sine omega t. And we had to use some substitution there as well. So if we take the same pendulum again and we ask ourselves, what is the acceleration after we started the timing at equilibrium, and the time was 1.1 seconds, we can calculate the acceleration. Again, make sure your calculator is in radians, check that you're getting the same answer, and we need to interpret the answer. So you end up getting this value, so it's a positive value. The acceleration is therefore going left from equilibrium. So it's started here in the middle, gone all the way right, and all the way, it's on its way to the left side, and it is slowing down, right? Finally, let's have a look at this one. So remember that the restoring force is always towards the middle, and so the acceleration is also always towards the middle. So if we just play this video clip, you can equate this and the acceleration, the top arrow. So acceleration at the ends is at a maximum, so full arrow, and the acceleration through the equilibrium position will be 0. So this equation, A is equal to A omega squared, only applies for the maximum positions. Be careful that you're not tempted to use that in any other case. So to remind you, there are two conditions for simple harmonic motion, where A must be directly proportional to y, and the acceleration is always directed towards the equilibrium position. So just all we're doing here is rewriting this equation, taking out the omega squared, putting in y is equal to a sine theta into this portion of it. And so we're really just showing you that this k constant value is actually omega squared. And finally, on your formula sheet, you will find there are 6 equations, and they look like these. The ones on the left, you only use those when the timing starts at equilibrium and moves either way. And on the right, these ones, which will be below the others on your formula sheet, are used when the equilibrium, or rather when the timing starts at the end positions.